you recognize that some of those questions track very closely the material in the lectures. We really do want you to understand maximum likelihood estimation and MAP estimation. It's going to be very helpful for the whole rest of the semester. So, also, I guess I want to say that I think you all know by now that videos of the lectures are available on the class website. We've also recently put some readings up on, if you go to the lecture schedule page on our class website, you'll see not only links to the videos, but also links to some readings. And one of the required readings for the coming week is up there, so please take a look at that. So far, really what we've done is look at Bayes classifiers. That is, how could we, instead of learning some deterministic function to predict y from x, learn the probabilistic function that maps from x to y, or p of y given x. And we've talked in detail about maximum likelihood and map estimation. Last time we brought up conditional independence. Why? Because conditional independence gives us, if we're willing to make that assumption, gives us a way to exponentially reduce the number of probability parameters that we have to learn from our training data in order to create what we were calling a naive Bayes classifier, which is a way of predicting p of y given x for any given x. So conditional independence was one of our key ideas for reducing the number of parameters we have to estimate from training data, and therefore making it even feasible to learn probabilistic functions like p of y given x. Remember before, when we tried to just make no assumptions, we noticed that if we're trying to even estimate a joint distribution with, I guess we decided 30 or more Boolean x's, we'd need 1 billion probability parameters, and there weren't enough people on Earth to populate our joint distribution for 100 features, for example. So it really is an issue, not just in terms of computational efficiency, but in terms of what we call sample complexity. That is, how much training data do we need in order to reliably estimate or learn these parameters? So that was the point of naive Bayes. What we're going to do today is look a little bit more at naive Bayes and at text classification using naive Bayes. In the upcoming homework, which will be out today, you'll get a chance to look at that in some detail. We're also going to look at the question of what if our attributes are not discrete valued? What if they're not Boolean? What if they're continuous, like the temperature? Then what will it take to turn naive Bayes into something that we can use for continuous attributes? Next lecture, we'll move on to some really closely related ideas. There's a very widely used algorithm called logistic regression, which has a kind of beautiful correspondence to naive Bayes. And so next time we'll be looking at that. So there's kind of a preview of what's coming up. But I want to start with, we've seen this, naive Bayes in a nutshell. Well, maybe it's worth saying. Naive Bayes in a nutshell just starts with Bayes' rule that tells us, given any particular example described by our x's, what is the probability that y will take on any given value based on Bayes' rule? And of course, the conditional independence assumption in naive Bayes tells us that we can replace this joint distribution by, no, don't do it. Who knows? By this thing, by the product of the individual probabilities of the x of i's, because we're assuming they're conditionally independent given y. And so, for example, if we want to just classify some new example that wasn't part of our training data and we don't know the y, then all we have to do is calculate the probability that y equals 1 and y equals 0, and then assign the y label that maximizes that probability. And if you look at this, you'll notice that this denominator really is just a constant independent of the yk. This denominator is actually summing over all the possible values of y. In fact, it's equal, that denominator is equal to just p of xi, because we're summing over all the possible values of y. So in a sense, if we want to maximize the probability, all we really have to worry about is the numerator. And so we can just assign the y, which maximizes the numerator. And so that's the key to naive. That's naive Bayes in a nutshell. So last time we trained a fortunately successful 8 out of 10 times on our test examples who were sitting in this aisle row of the class. And you saw the details on how we trained that, but we didn't get a chance in class to go through the details of how we would classify a new example. So I just want to start by quickly doing that, where I volunteer to be the test example. Okay, so it turns out we want to predict whether I live in Squirrel Hill. I'm not telling you until later. But I will tell you that my value is D. Yes, I did drive, in fact, today to CMU. G, no, I have not shopped at the Squirrel Hill Giant Eagle since September. And B, yes, no, my birthday is not before July 1st. Okay, so I'm a new test example. Obviously, I was not part of the training data. And so if we want to predict what's the probability, given those features, that S equals 1, that is, that this example does live in Squirrel Hill, then what I've done here is just written out the ratio, the Bayes rule, right? Remember, I've just written out this. So the probability that Squirrel Hill equals 1, given my features, is just the prior probability that Squirrel Hill equals 1 times each of the individual conditional probabilities over this denominator. Okay, so if we do that here, you see that's exactly what I've got. Here's the prior, that Squirrel Hill equals 1, times each of the conditional probabilities under the assumption that S equals 1. And then the numerator is that very same quantity, right? This is identical to this, plus that same quantity, but now assuming that S equals 0 instead of S equals 1. Right? So that's exactly what we said. If we make the conditional independence assumption and apply Bayes' rule, this is exactly what we said will give us the probability that S equals 1 given these values. Okay. So from the training data, you can see here that, in fact, we have calculated everything that we need. Every one of these terms is available from the training that we did last class. And so, for example, what's P of S equals 1? Well, that's just 26 over 102. The probability that D equals 1 given S equals 1, that's just 3 over 26, and so forth. Okay, so I could go through and do all these. Let's do one more. The probability that G equals 0 given S equals 1, oh, well, that's 0. And then there are a bunch of other terms that you could fill in easily. Okay, so what is the answer here? What is the quantity that this evaluates to? 0. Because, of course, it only takes 1 0 in a product to make the whole product 0. So it doesn't really matter what all these other numbers are, does it? We just have a 0 here, so the probability, according to this trained model, that I live in Squirrel Hill is 0. And therefore, the probability that S equals 0 is 1, according to this classifier. And now I can reveal the truth. I live downtown, so I don't live in Squirrel Hill. So I'm correctly classified by this classifier. Okay. So I just wanted to take that moment to go through this so that you see exactly what we're doing here. The training data, the training procedure just calculates all of these terms. Those are all the terms that we're ever going to need to classify any example, no matter what these values are. Right? And all I did was just expand that expression that we said from Bayes' rule plus the naive assumption that these terms are conditionally independent given S. And then given that, this small number of probability estimates is all I need for classification. Okay, the same will be true of your own naive Bayes classifier in the coming week. All right, so any questions about that before we leave it? Yes?
So it is possible for probability to, I mean, P of S equal to 1 and P of S equal to 0, both of them can be theoretically 0, right? Because right now we have one term which is 0 here. But it is also possible for you so that both of your probabilities are 0.
That's a very good point. So if you didn't hear this comment, this very astute comment, he said, depending on our training data, we might actually find that the probability that S equals 1 is 0, and we might also calculate that the probability of S equals 0 is also 0. Right? Meaning that some of these terms might have ended up being 0. Like we did, in fact, decide that the probability that you don't shop at Giant Eagle if you do live in Squirrel Hill is 0. We might have also, depending on the data we had, we might have also found that the probability that your birthday is late, given that you don't live in Squirrel Hill, we might have somehow got a sample of data where that happened to have 0 occurrences. And therefore, our maximum likelihood estimate would give us a 0 there too. And so then in the problem there of classifying me with that, this would be 0, this would be 0, and this would be 0. So I'll have a 0 over 0, which is hard to calculate. Okay, undefined really. Okay, so that's a good observation. And that's another argument for using map estimates instead of maximum likelihood. In fact, one of the unintended consequences of this example from last time is it's a great illustration of why map estimates are usually a nice idea unless you have a huge amount of training data. Right? This MLE, the maximum likelihood estimate that we got for this, essentially concluded that it's impossible that somebody who lived in Squirrel Hill would not shop in Giant Eagle. Just happened to be true of the sample of data, but I'm sure if we were to interview everybody who lives in Squirrel Hill, we'd find somebody who doesn't shop there. Okay, and having a 0 is a particularly bad value because it just completely dominates the conclusion. Okay. And map estimates would, if we added in some hallucinated examples, say one hallucinated example for every vote that we took, then this would at least be, instead of 0 out of 26, with our hallucinated example, we'd get a ratio of 1 out of 27. And so it would still be a very powerful term, but it wouldn't eliminate the votes of everybody else. Okay, so I want to take one other view of naive Bayes. This is a kind of interesting way to think about it. Suppose I'm interested in what's the form of the decision surface. That is, if we were to plot the x sub i's on different axes and plot each of you training examples and test examples as points in that n-dimensional space, and then if we were to train our classifier and show the region of the space where it labels things positive, where it assumes y equals 1, versus negative, where it assumes y equals 0, what's the shape of that surface going to be? It's actually kind of an interesting question. In fact, think about in the shower sometime what the shape of that decision surface is for decision trees. And every algorithm that we go through, think about, in the shower it's nice because you can draw on, the steamed up thing. So, but think, you should ask this for every algorithm that we cover. Okay, so let's ask it here. So one way I think about naive Bayes is this way. We can certainly calculate this probability and this probability using naive Bayes. There's the, in fact, if we look at the ratio of those, then of course we're going to classify the example as y equals 1 depending on whether this quantity is greater than 1. If the probability that y equals 1 given x's is higher than the probability that it's 0, then the ratio will be greater than 1, and we'll classify it as a 1. And since the probability of y, remember, given x, is just Bayes' rule, probability of x given y, probability of y, over probability of x. If I take the ratio of these two, the denominator, I get these two expressions with y bound to 1 and 0, but the denominator p of x doesn't really, it just cancels out if I take the ratio. And so the ratio is really just the numerators. And that's what I've shown here. Okay. So I'd also like to take the log of these to make it a little easier to think this through. So if I take the log of this ratio, let's see, if I want to know whether the ratio is above or below 1, what does that mean? I want to know about the log of the ratio. What's the log of 1? Right. So I want to know if this log is above 0. It's the same test. But then I can take this product and let's see, the log of the product is the sum of the logs. So then this becomes the log of p of y equals 1 over p of y equals 0 plus, now this is no longer a product but a sum. Okay, I'll write it that way. Plus the sum over I of log of p of xi given y equals 1 over p of xi given y equals 0. Interesting. Okay, so now when we go to classify any given person, like me in the case of do I live in Squirrel Hill, we can think of the final decision as yes or no as being this linear sum of terms. This first term is a constant. It doesn't matter what my features are, right? This is just the ratio of the priors. And if the prior on y equals 1 is greater than the prior on y equals 0, that'll be a big number. Otherwise, it'll be a small number. Okay, that makes sense. The higher that ratio is, the more likely it is that the sum will be above 1 and all be And then these terms are looking at this is the sum over each of the individual features. So there's also, so we can think of this decision that we're making with naive Bayes as the result of a linear sum of contributions, one of which is independent of the features, just depends on the priors. The others, each feature contributes one term in the sum. Okay? And in fact, if you work this out, you'll see that this turns out to be actually each of these terms is itself a linear function of the value of xi. If xi is a Boolean value, for example, then this expands to just a sum of basically a linear constant that goes with the value of xi, 1 or 0. So you can work out that yourself if you express this in terms of the actual value of x. Okay, but so the bottom line is this is, I guess I should say, if the x sub I are Boolean, that is, they can only take on values of 1 and 0, then the decision is thresholded that is this quantity above or below 0 linear function of the x sub i's. Okay, so it would actually be a good homework question to ask, or a good midterm to ask you to flesh this out. Assume that x sub I equals the value a, where a can be 1 or 0, and then just you can easily work out that these terms are some constant times that value a. Okay, so that was just a side comment about naive Bayes, but we're going to keep doing this for our various learning algorithms that we talk about. We're going to look at what's the shape of that decision surface. All right, let's move on to using naive Bayes to classify documents. For example, emails. We might be interested in building a classifier that tells us yes or no, is this email suggesting an attachment is there? And that way our email reader could warn us if we write such an email but forget the attachment, or spam and so forth. So if we're going to apply naive Bayes to this, then the key question is really how are we going to represent a blob of text as a set of discrete valued x sub I features. And probably many of you know already that a common technique for doing this is is to turn the document into a set of variables that reflect the bag of words that's in the document. But let's drill down on that, and actually we'll see that there are a couple different ways that we could do this. And in practice, if you're applying one of the algorithms that we learn about in this course to some problem, some real application like email classification, often the very first question that you'll have to face, the first design step, is to figure out how can we take this real problem and convert it into the formalism that's required by our learning algorithm. In our case, for naive Bayes, we need a set of x sub i's, random variables that represent this document. Okay, so the key question is, we're going to say spam or not will be y. That's 1, 0. That's easy. And then x will be our document. It'll be a collection of random variables. But what exactly is each, like, what should be x sub 1? Suggestions? Yes?
xi could be like Boolean variable variables to describe whether a specific word has shown up.
Okay, so the suggestion is we could make each exaby a variable that indicates whether a particular word shows up or not in the document. And I like that idea. In fact, that's a common way of doing this. And we could do that. We could say exaby, okay, it's going to be a Boolean variable. Whenever you define your exabys or any random variable in this class, never, ever, ever forget to ask yourself, what are the values this random variable is actually going to be able to take on? That determines, if you're sloppy about that, you'll confuse yourself all the way through. Okay, so we could define exaby as a Boolean if the ith word is in the document, and otherwise it'll be 0. And for example, we could have the word pleased, and x sub pleased is 1 for this document because I see it up there as the third word in the email. So if we do this, how many x's will we have? How many exabys? Okay, so I'll tell you that my linguist friends, or psycholinguist friends, tell me that most adults who speak English fluently have a 50,000 word vocabulary. So they tell me that you and I probably know 50,000 different words. So roughly speaking, there could be 50,000 of these different exabys. Boy, aren't you glad now that we're talking about naive Bayes instead of learning the full joint distribution over 50,000 variables? How many will we need? If we have 50,000 exabys, how many probability terms will we need? 2 times that, plus 1 for the prior. So we'll need 100,000 probability terms estimated, plus 1 for the prior. Okay. That's actually not so bad. Well, it depends on how much email we have to work with. But if we have, say, 10,000 emails to train it on, I think we'll be OK, because they're, on average, going to be probably hundreds of words in each email, and so we might have a chance. OK, so that's the way we could do it. Here's a different framing of it. We could instead say that xi is a random variable that represents the value of the word that's in position I in the document. Okay, so instead of saying we'll have a word for an exaby for every word in the vocabulary, and it'll have a value of 1 or 0, we could instead say, I'll put a random variable whose value is whatever word exists in the first position in the document. The word is I in this case. So x sub 1 would be I, x sub 2 would be am, x sub 3 would be pleased, and so forth. Okay. That's kind of interesting. Okay, and how many exabys would we have in that case? I guess it'll depend on how long the document is. I guess we could just say we'll take the longest email in our data set, and that'll be how many exabys. And maybe we'll define a symbol null or empty symbol in case the email isn't long enough to have one of those. OK, but now, what if we, in addition, we can make our problem kind of, we can make another simplifying assumption. What if we assume that the probability that x sub I will take on any of its 50,000 possible values, suppose those are independent, identically distributed through the document. That is, we assume that, just like we assumed when we do the coin flips many times, we assume the outcome of each coin flip was independent of the other coin flips. So this meaning the probability of any given word in any position is independent of the words in the other positions. And that they're identically distributed. We're flipping the same coin. In this case, we're saying just the probability that pleased occurs in position 3 will be no different from the probability that pleased occurs in position 14. It's like the outcome of the flip is the same no matter whether it's the 3rd flip or the 14th flip. Yes?
But don't we obviously know that not to be the case?
Oh, sorry, I was...
Seeing as this is a language and written to know that will obviously not be true.
Thank you. Right, this is a bizarre assumption because words never start with, well, I'm sorry, emails never start with, I can't think of a word that an email couldn't start with, but there are a lot of sentences that start with a determiner. For example, it's more probable that a sentence will begin with a determiner like the or a, and less probable that it'll start with a verb like drive, although it could. So it's clearly not true that these are identically distributed. It's also not true that they're conditionally independent. And neither was it true in our first assumption, in our first framing where we had x sub I be a 1 or a 0. If the word machine is in the email, then it's probably more probable that the word learning will be in the email too than if machine isn't in there. Okay, so words go together. They're not really independent. So why are we even talking about this? We're talking about it for 2 reasons. One is we don't really have a choice in the matter. If we have 50,000 variables, or even one variable with 50,000 values, we've got 50,000 parameters we have to estimate. If we do make these assumptions, and if we don't, we have 2 to the 50,000 parameters that we have to estimate. So we don't really get a choice about whether we make some simplifying assumption. Now, we do like to make realistic simplifying assumptions. And this one is really obviously false, and I agree with you on that. So my second justification for doing this is a lot of people do this, and it works. So other models that make more realistic assumptions may work better, but this one in practice is surprisingly effective. And so that's a reason that we're looking at it. But I like your point that these assumptions we're making are not really satisfied in practice. But we're upping in a hard place because we've got to make some assumptions. Otherwise, we're going to need 2 to the 50,000 distinct parameters that we're estimating times 2. That won't be good. OK, so let's go with this idea, the framing number 2, where each random variable corresponds to what word appears in the ith position in the document. And if we make that IID assumption, then it's actually isomorphic to the problem of, we could say that these documents are generated by rolling a die, that has not 6 sides, but 50,000 sides, a different word printed on each side of the die. And maybe the faces of the die are a little different, like for rare words, the very small face, and for frequent words, a big face, making it more probable that it'll end up on that face. But effectively, once we make this IID assumption, it's like saying the document is generated by rolling a 50,000-sided die n times, where n is the number of words in this particular email. Okay? And so if we do that, the observed, so now let's go back to rule number 1. Always say what your random variables are and what they can take on. So these can take on each of 50,000 words as their values, each one. And so if I roll that 50,000-sided die n times and create a bag of n words, and I count how many times each word occurs out of my 50,000 distinct words, that's like flipping our coin 50,000 times and counting how many times it was head or tails. But now instead of only 2 possibilities, we have 50,000, right? And we talked about that. So this, when we talked about map estimates for coins, we could have talked about map estimates for die. And let's do this for a second. So if we have a die and we roll it n times, or k times in this case, I'm sorry, it has k sides. So the dice, k sides to this. For a regular die, there might be 6 sides. For the die we're going to be rolling, it's going to have 50,000 sides. And so we can roll it n times, once for each word in the document. Essentially, that's what the document, what we're treating the document is the set of n die rolls. Then the probability of the data given theta, where theta now is the vector of theta 1, theta 2, theta k, where theta I is just the probability, that the die turns out on side I. Then if alphas, just like before, are the counts of how many times we roll a 1, and alpha 2 is the count of how many times we roll a 2, if we were to stop there and only have a 2-sided die, it will be exactly the same as our coin flip. But we could continue and say, well, this die has 6 sides, or k sides. Then the probability of the data given that is just the probability of a 1 times, raised to the exponent of how many times we observe the 1, and so forth, exactly analogous to our coin flip. And then we could make up a prior, which we'll call a Dirichlet prior. This is actually just the generalization of the beta prior that we use for our coin flip. How's it different from a beta prior? The beta prior just had a theta 1 and a theta 0 for heads and tails, or a theta 1 and a theta 2 for heads and tails. Here we're going to allow k thetas because there are k sides. But if we set k to 2, this is the beta prior. And if we set k to something else, well, it's called a Dirichlet distribution, but it's the same form. We have to make up these betas which stand for the number of hallucinated flips that we're doing that show up with that side of the die, minus 1. Okay, and so then if we try to get this by multiplying the prior times the data likelihood, we end up with another Dirichlet distribution where now the theta, but now the exponents are the alpha sub i's plus these beta I minus 1. And then when we solve for the map estimate, it looks just like our coin flip map estimate, where we have the observed number of times the die shows up side I, plus this quantity, which represents the number of hallucinated examples that we put into our prior for side I. And then the denominator is just the total number of flips observed plus hallucinated that we think of. Okay, so this is just the simple generalization of the 2-sided die to a k-sided die. And now we're ready to do naive Bayes document classification. Because remember, we're saying that we can think of a document as having been generated according to this distribution where we roll a 50,000-sided die, once for each position. And that's the probability model that we're going to use here. And so given this, this tells us how we will train our system. Just like in class when we did the Squirrel Hill example, we were essentially saying we had a 2-sided die that we would flip for each of our x sub i's that went with the Squirrel Hill equals 1 condition, and we had a different die or coin that we would flip that went with the Squirrel Hill equals 0 condition. And all we could observe were the training example were the outcomes of those, but from that we had to guess whether that went with the distribution for Squirrel Hill equals 1 or 0. And here we're going to do the same thing. So we have to estimate for each of our features, each of our random variables, what's the probability that it will take on its ith value by counting up the observed plus hallucinated counts. And so a bag of words model is nothing more than that. So for example, here's a document. Here are the counts of different words. This vector is 50,000 features, 50,000 words long. I've left out some of them. But here are the counts of number of times various words occur. These are the alphas, the observed number of times that the die showed up with the word gas when we rolled it. And the number of times turns up twice with the word about. So the bag of words counts are exactly those alphas in our MLE and MAP expressions, provided we define our random variable to be the coin flip to be which word shows up at each given position, and provided we make that IID assumption. Okay. So the point of this discussion is to show that we could start with this probabilistic formalism and the rules of naive Bayes. We can apply it to this problem of document classification, but to do that, we needed to take this application and somehow phrase it in the terminology of our formalism. And since we're using naive Bayes, what that means is we have to define a set of random variables that are the x sub i's in our classification problem. And this is actually the most common formulation for naive Bayes applied to text classification. Okay. So again, these are really our alphas. Okay. So if we want to use a map estimate, which I think we do, for the same reason that we got into trouble with Squirrel Hill by using MLEs, then we can think of, here's our formula we just agreed is the map formula. We can also think of that as for each probability term we're interested in is just the probability that a particular, for each word we have a probability term of the probability that when we roll that 50,000-sided die, we'll get a particular value. And again, we have two of these die, one that goes with generating spam emails and a different die that goes with generating non-spam emails. And we're assuming there will be differences in those probabilities. But assuming that we're just working with one of them, say spam, we're going to want to know, among our spam documents, we want to estimate the probability that X will be aardvark, for example. And so our thing here says, look at the ratio of observed plus hallucinated aardvarks to the sum of all possible, to the sum of all our counts, observed and not. By the way, you probably noticed this before, but I kind of flip between saying the number of hallucinated examples and beta minus 1. So the way we defined our beta or our Dirichlet distribution, these are. The number of hallucinated examples is actually the beta value that we chose, minus 1. Technicality, but you probably recognize that technicality from the homework assignment due today. So what betas would you choose? Like for aardvark, what beta sub-aardvark should we use? Or how many hallucinated aardvarks do you want to add to our priors?
So we can look at something like 10,000 documents and see what is the frequency of having that artwork, something like that.
Good. I like that. So we could just take a huge amount of text that we assume contains every word at least once, and then just look at their relative frequencies. And then we could say, OK, we'll assign a non-zero number of hallucinated aardvarks. But maybe what we'll do is just look at 100 million web pages, how often get the counts there, ignoring whether they're spam or not, and just saying that gives us a kind of baseline estimate of word frequencies in general. And then we could say, OK, we're going to take those frequencies and normalize them so that they sum to, I don't know, 50,000. So that on average, for each of the 50,000 estimates we're doing, so that the number of total hallucinated words will be 50,000. And then the number for each individual word will just be its relative proportion in those web pages that we searched. That's a very reasonable way to do it. A cheap way to do it, if you don't want to take the time to do that, is just say every word is equally likely, equally probable. Just assign one hallucinated aardvark, which means a beta of 2 for each word. So that would be a uniform distribution, much less reasonable given the true nature of language. But remember that our estimates that we're going to build are going to hopefully have more observed counts than one anyway. So that uniform distribution is enough to keep us away from having zero estimates that probabilities are 0. And they'll be dominated by the observed counts in many cases anyway. But the best way to do it is to actually look at the real word frequencies. And that's a good prior. OK? So now we can do it. Here's our naive Bayes algorithm for discrete exabytes that are no longer Boolean, but just have a discrete number of values. In the case we're talking about here, each exabyte has 50,000 values. And so we're making this additional assumption that the word probabilities are position independent, that is, their IID. But now our training procedure for training naive Bayes is just like we did in class, in a sense. We need to take our training documents. Somebody gives us spam documents and non-spam documents. From that, we need to estimate the prior, that y will equal spam or not equal spam. And for each value of each attribute, we need to estimate the probability that the random variable will take will take on its jth value, given that y takes on its kth value. In this case, y can be 1 or 0. J can be, well, there are 50,000 different values that x sub I can take on. And then if we make this additional assumption that they're IID, well, we don't actually have to estimate this separately for each position. And so we're just working with the alpha counts. Okay? And then after we train, that's just like when we train the Squirrel Hill classifier, except that instead of 2 outcomes, there are 50,000 outcomes. And now, if we want to classify a new document, we just have to look at the values of the words in its bag of words and calculate the probability that we'll get those observed values times the prior, and then take the y that maximizes that. And if we follow the notation we used up there, we said, well, we're going to use pi sub k to be the prior that y takes on its kth value. Then if these are the specific terms that we were estimated during training, then we just have to multiply together those. And here, based on the observed values of x new. Just like when we classified me in the Squirrel Hill case, we looked at my observed values to pick out the right subset of these IJKs.
So in this case, why is the category that we want to put the documents in, right? The spam or not a spam?
Right. Where are those? The categories here are spam or not. And so they show up here. Okay? All right. So does this work? In fact, it does. Here's an experiment that we did where we had newsgroup articles in 20 different news groups. Pretty diverse, but they kind of fell into religion-based ones, techno, I don't know what this one is, computery, but 20 news groups. And instead of trying to decide whether a document is spam or not, we trained it to decide which of these 20 news groups did it come from. So now Y has values 1 through 20. That's OK. We can apply naive Bayes to any problem where Y has a finite discrete number of values. Yes?
But this would make that my spam folder classification is same as yours.
Oh.
It should be different for me in different ways.
That's right. So this is a comment about spam filters, which is an on-target comment saying that we really would like, I might have a different notion of spam than you do, and we'd like to have spam filters that respect to that. So how do we achieve that? Well, it's really a matter of what training data we give to the system. So if we want a spam filter for you, we should give it training data that you have labeled. If we want one for me, we should give it data that I have labeled. There's an interesting opportunity there if we want it to learn both of those, because maybe it learned your spam filter first. Hey, we could use that as some kind of data to getting a prior for my spam filter estimates. Right? So my spam filter should depend in the end on the alpha counts from my data. But maybe we should put in some beta counts for our prior based on other spam filters. If most people think that the words free $1 million indicate spam, then maybe we should use that also as a prior for the spam filter for a new person. In fact, there's a whole burgeoning area of research called transfer learning, which is really exactly about the research question of, if I have trained different classifiers and I have another one now to train, and I can make some kind of assumption that this new classifier is somehow related to the others, then what are good algorithms for using those other learned classifiers to bias the learning of this new one? And people, you can think of all kinds of problem structures where that's the case, but the family of spam filters that each of us would like is a kind of beautiful example of that. Good. Okay, so anyway, back to this example. Here, we're just trying to classify which of these 20 labels, news groups, any given document came from. And so, in fact, you can train a naive Bayes classifier on this problem and achieve 89% accuracy on a separate held out set of documents that were not part of the training set. Now, how good is that? What if we guessed at random, what would be the accuracy? 5%. There are 20 possible values Y can take on. If we're just randomly guessing, we'll be right by accident 1 time out of 20. So the chance level accuracy is 5%, but here, 89 times out of 100, we get the exact right 1 out of 20 choices. So this is a pretty powerful method. In fact, here's a plot showing how that accuracy, and we're interested here in the one that's labeled Bayes. That's this one. Performs as a function of how many training examples we show it. And then the test accuracy is based on separate withheld data. Okay? So you see that, as you might expect, the more training data we use, the better the accuracy gets. And, but even with 100 training examples, that's not very many. That's 5 documents for each of the 20 news groups. 5 examples of each of 20. We're already getting 35% accuracy, even though we have to choose one of 20 values, and chance is down here at 5%. Oops, 5%. Okay. Okay, so any questions about text classification with naive Bayes? You'll have plenty of chance over the next week to play with this. Okay, I think it's pretty straightforward. Conceptually, I think you've got it, and it'll be fun to get a chance to actually play around with some real data and see what happens. So what I want to do now is move on to a more conceptually interesting question, which is, well, what if our x sub i's are continuous instead of discrete? So for example, I might have image data, like brain image data that we've been using in our own research group, where the pixels in the images are continuous values. In this case, they are continuous values from an fMRI machine, which is measuring the magnitude of brain activity at each of 20,000 locations in your brain. And those are real number values at each of 20,000 places. So we can think of an image like this as a vector of x1 through x 20,000, where each of those x sub i's is some real value which reflects the brain activity at the ith location in your brain. Okay. Or similarly for a photograph, if you're trying to train a photograph classifier to tell if your mother's there, then you could do the same kind of thing. Or any real value. Okay, so we'll use this to illustrate. So what can we do here? Suppose we still want to use naive Bayes, but we have continuous values for our x sub i's. Well, here's our naive Bayes equation again. And so you can see that, let's suppose y is still 1 or 0. For example, we're taking an image of your brain activity and we're trying to tell, are you thinking about the machine learning class, yes or no? And so it's still a discrete y, but now we have these continuous x's. And so the only thing we have to change, here we still have our Bernoulli distribution, yes or no, y is a Bernoulli variable, 1s and 0s. We can use our map estimates or our MLEs and handle that fine. The only thing we have to change is now we need a way of defining a probability distribution where x sub I is real valued. And so the most common way of doing this is to use a probability distribution which is called Gaussian or a normal distribution. Those are synonyms. And many of you are familiar with a Gaussian distribution. It looks like this. We say that the probability density for any given value, any given real value x, is this quantity. But if you plot it, here I have x on the horizontal axis and probability of x on the vertical axis. So for this particular distribution, you can see the probability density is highest when Oh, we can do that. When x equals 0, and then it falls off as x gets away from 0. But in fact, in general, the Gaussian distribution is defined in terms of two parameters, a mean, mu, and a variance, sigma. The mean defines where the peak of this distribution is. So the one I've plotted here has mu, the mean. I set that equal to 0 when I defined this plot. And then sigma tells us the variance, how wide that bell curve is. And when I plotted this one, I set sigma to 1. So if you set mu 0, sigma 1, you get this distribution. If you set mu equals 2 and sigma equals 1, you get the same shape, just translated 2 units to the right. And if you set sigma to some higher value, then the bell gets wider, lower value gets narrower. So it's basically Gaussian distribution. I think many of you have seen this before. Okay, but basically the peak is where mu is, and the variance is the distance, the width of the curve. And so we can pick mu's and sigmas and define different Gaussian distributions. And that's exactly what we're going to do to train a Gaussian naive Bayes classifier. Instead of counting and calculating the probability that our coin ends up heads or tails, we're going to estimate the mu and the sigma for each of our real valued x sub i's. And that way, we'll be able to just carry on with our naive Bayes classifier. Given a new example, we'll be able to say, what's the probability, given the Gaussian associated with Squirrel Hill equals 1, what's the probability that your height will be 5.173 meters, or feet. And so instead of calculating that based on these estimates of coin flip, Bernoulli binomial distributions, we'll just use a Gaussian instead. So now you see something about the generality of naive Bayes too. We can actually use any probability distribution for the individual features. We just happen to have started with these Bernoulli variables and estimating probabilities for Bernoulli distributions. But we could use a Gaussian distribution if we like. We could use any kind of distribution that we think is appropriate for the variables that we're dealing with. OK, so let's ask this. So again, here's our equation for a Gaussian distribution. And just like before, naive Bayes requires that when we train, we take our training data and we somehow come up with the ability to estimate the probability that x sub I will take on any given value, given the y that we're using. And so what we're going to do is we're going to estimate a number of different Gaussian distributions, a different one for each. Let's look at these means here. Oops. These means, for example. So we're going to get a different mean for each I. That's this I, for each feature. So back to the brain image case, that means for each of the 20,000 locations in my brain, those are different x sub I readings. There might be, given that I am thinking of machine learning or not, I'm going to learn a different mean for each location in my brain and for each value of yes or no for y. Am I thinking about machine learning or not? So 20,000 locations, each of them I'll have a mean for when I am thinking about machine learning, when I'm not. So I'll have 40,000 mu's. 40,000 different probability distributions of the form, what's the value at location I given label k. And then similarly, I'll have a different sigma for each of those as well. Now, it turns out that often in real cases, again, if data is sparse, people often estimate these sigmas to be independent of the label. You don't have to, but it's one assumption. In fact, in the case of fMRI and brain images, it turns out to be a kind of reasonable assumption, because where does the variance, if I repeatedly measure the activity in this one spot in my brain while I'm thinking about machine learning, I might get different readings at different times, but many of those are actually due to just noise in the scanner that's collecting the data. So if I assume that noise is a kind of constant effect, independent of whether I'm thinking of machine learning or not, it's the same noise in the machine, then it's realistic to assume that the variances here will not really be sensitive to what the value of y is. And so if I'm in that kind of a problem, and in fact, when we do this for fMRI, that's typically what we do. Or you can say that it's independent of the xi, that the noise is the same across the entire brain. Or you could say that it's independent of both. And obviously, the stronger the assumption you make, the fewer sigmas you have to estimate, meaning that if your data is sparse, the less likely you're going to get in trouble by not having enough data to make those estimates. All right, so then this leads to the Gaussian naive Bayes algorithm, which again looks just like our other one. That is, during training, what do? Well, we have to estimate the priors on our class variable, and we have to estimate whatever parameters are needed to define the conditional distribution of each of the x sub i's given the y's. Since we're using a Gaussian distribution, this last line is different from the discrete case, because now we have to estimate a separate mean and a separate variance for each x sub I and y sub k. But otherwise, it's exactly the same. And similarly, when we classify a new example, it's exactly the same. We just want the y that maximizes this. And in this case now, for this probability, if we get a new brain image, we just have to take our normal distribution and apply it to ask how probable would that observed brain value at location I be, given that it was generated by the mean from distribution for feature I, but for y equals k. And we'll try this out with k equals 1 and 0, thinking about machine learning and not. And then we'll see which one gives us a higher probability, and we'll make the assignment. Okay, so that sounded almost identical to what we did for text classification and for Squirrel Hill, because it is. The only difference is that now we're using a Gaussian distribution to represent these individual feature conditional distributions. And if you prefer to use a Poisson distribution because you have values that never go negative, that's good. You could put in a Poisson and build a Poisson naive Bayes classifier instead. Okay. How do we estimate these parameters? Again, we can have maximum likelihood estimates or map estimates. In this case, maximum likelihood is a pretty good, pretty reasonable thing to do. For example, we need to estimate for every ith feature in kth class, value of y, we need to estimate the mean and the variance. The way to estimate the mean is just to take the sum of all the x values that happen to come from training examples where y does equal the kth value, and literally just calculate the mean of the brain activity in the ith location from examples that are labeled as y equals 1. And separately, you'll compute the mean for y equals 0, and similarly, the variance. Variance is just the square of how far the observed value is from the mean. That was telling us how wide the Gaussian is. So this is pretty straightforward. And let me skip this one and just look at this in practice. So this actually, again, works remarkably well in practice, despite the fact that, again, the naive Bayes assumption is not really satisfied in your brain. It's not true that whether there's activity here is completely independent of all the other activity in your brain. That's actually, brains are not that random. So there is some correlation across the brain of where activity is. But despite that, this algorithm actually works pretty well. So for example, we have used it quite successfully to classify brain images according to which word was the person reading at the time that we took the brain image. So we put people in a scanner, we showed them words like house and palace and hotel, or tool words like hammer and screwdriver and saw. And then we tried to train a classifier to look at their brain activity and tell yes or no, were they thinking about a tool word or a building word at the time that we captured the brain activity. So here we just map it into, oh, I see. Here I have an example where it's house or bottle, but same deal. And this top row shows part of the three-dimensional brain image. So of course your brain is in 3 dimensions. We capture with fMRI a 3-dimensional image of that neural activity. And here what you're seeing is 4 different horizontal slices of that 3-dimensional image. There are a total of about 25 horizontal slices, because we're doing a resolution of a couple of millimeters. And as this thermometer says over here, where you see bright red, there's high neural activity. Where you see this color, it's kind of average neural activity. When I say average, I mean no different from when you were just lying in the scanner waiting for the word to appear on the screen. And if you see darker, it actually means it's suppressed from the background mean activity. And these images look a little funny. That's because we're only interested in cortex part of your brain. We're not interested in where the cables are, the white matter. And so the dark blue is really just part of the brain we're ignoring. Okay, but what you see there on top is actually an image when somebody was looking at the word bottle. And that's what brain activity looks like. By the way, the top of the picture is the back of the brain. The bottom of the picture is the front of the brain. And so you can see there's blotchy, high red activity toward the back of the brain when this person looked at bottle. So we train a classifier. In fact, oh, this is actually the mean of all the times that they looked at bottle. So this is a plot of the Muse for each of not 20,000, but probably 3,000 different locations shown there. Those are the learned means, the Muse, for the Gaussian distribution that we assume controls each neural activity in each of those locations, conditioned on the word being bottle. And there will be a different set of means that we estimate from examples where the word is not bottle. And so if we train the naive Bayes Gaussian classifier that way, this actually works remarkably well. If we train on participant 4 and then test on new data not part of the training set for participant 4, we get very high accuracies. For some participants, it does not work as well. But in all cases, it's better than the chance 50% level from random guessing. Furthermore, once you get the idea that you can train a classifier to decode basically mental state from observed neural activity, one of the interesting things scientifically that you can do is you can ask, well, where is that brain activity that's actually encoding the difference between house and bottle, for example. Where's the neural activity that's encoding house? And one way to do that is to look at these, the learned muse, and you can see, well, the red blotches are where the neural activity is exceptionally large when you think about bottle. Another way we can do it is we can train a classifier using not the whole brain, but a small fraction of the brain. So what we did is we trained a little, even though we have 20,000 voxels, three-dimensional pixels in our brain image, we trained a classifier that only used a little Rubik's cube, 3 by 3 by 3 voxels, 27 voxels. And we moved that Rubik's cube, so that's about 1 cubic centimeter of brain tissue. And we trained a different classifier for each cubic centimeter of brain tissue to see, well, what if we only get the information from this part of your brain? Can we decode, does that actually information there encode or not encode the distinction between whether you're thinking about the meaning of a bottle or a hammer? And so when we did that for, in this case, tools versus buildings, we could then plot the locations in the brain where that little 1 cubic centimeter of brain tissue does actually allow decoding, sometimes with almost 80% accuracy, whether you're thinking about tools or buildings in this case. So it becomes kind of an interesting case study for 2 reasons for our class. One, the main one is that here's an illustration of how we can do Gaussian naive Bayes classifiers in the case where our variables are continuous. But it's also kind of interesting as a tool that has really become much more popular over the last 10 years in the field of neuroscience for trying to analyze brain image data, because it gives us, machine learning here is giving us an opportunity to go from observed neural activity, which is interesting to neurosciences, but to go from that to the encoded information that's in the brain. So you can think of each of these classifiers that we're training as a kind of training of a virtual sensor of the information content in the neural activity. So that's an example of how machine learning can change the landscape, actually, in this case for a neuroscience question, by allowing us to train these. I really do think of this as a virtual sensor whose input is observed brain activity and whose output is the information encoded in that activity. Okay, so we're done with naive Bayes. Here's what I think you should know. First of all, naive Bayes really was our chance to take a first look at Bayes classifiers. And it turns out it's a very rich family of them. Naive Bayes is over in one corner, but a very useful corner. Naive Bayes is really based on this idea of conditional independence. You need to understand that and why it's important. Of course, it's important because it allows us to reduce dramatically the difficulty of estimating probability distributions if we happen to be willing to make that assumption. And then you should understand how to train those with different kinds of estimates and with discrete or continuous. I added in the slides a few questions that you can think about. These are not homework questions, but I think they're useful questions to think about. These are the kind of questions that I think about when I come back to make up a midterm. In midterm time, I think, okay, what were some of the key concepts that we covered? And what are some questions that we could ask on the midterm that would be answerable if you really understood those key concepts? So I'm not saying these will be on the midterm, but they came from they're generated from the same probability distribution as midterm. Okay, so don't forget to pick up the new homework assignment today. Don't forget to turn in the old homework assignment. And We'll see you next time.